Please. Hi, welcome to Points Topology, Part 2, Live Session 4. This is Shovik and walking from his last week. And this is the fourth live session for this course itself. Just please hold a moment. Let me switch off the fan. So, this is the fourth session of this course. Okay. So, today we shall start the assignment problems. But before doing that, let me know, do you have any particular question or any doubt from the last session, or do you have any doubt from the assignment sessions? Please let me know. If you don't have any doubt, then also please let me know so that we can proceed further. So wait for a couple of minutes and let me know, do you have any question or doubt? Please take your time. Hi, Sham. If you do have any question, please let me know, or else. Okay, before starting, let me know, am I audible and is the screen visible to you properly? Hello, Sham. Am I audible? Okay, it seems there is some issue. Hello, Sam. Am I audible, or is this internet issue? Okay. Thanks for the confirmation. Okay. So, okay. So, please let me know, do you have any question or doubt from the previous session? Or else we can start solving problems from the previous assignment itself. Please let me know. Okay. Okay. Thank you for the confirmation. Thank you. Okay. So, in the meantime, let me write the questions. Okay. So since there is no questions floating around, so let me start the first question. So the first question is that let f R3 to R be a C1 function and P x naught y naught z naught be a point such that f of x naught y naught z naught equal to 0. Now the question is that consider the following statement. The statement is as, okay, statement. Statement there exists row greater than 0 and a unique C1 function g from B row x naught y naught to R such that g of x naught y naught equal to z naught and f of xy comma g of xy equal to 0, that is z coordinate replaced by g. Now the question is that, okay, now the question is that state whether s is true or false in each of the following cases. Case A, that f of xyz, that is equal to x square plus y square minus 2z square and p is equal to 1 at the point 1 1 1. B is equal to f of x comma y comma z, that is equal to 2x square minus y square minus z square. P is equal to 1 1 1. C is equal to f of x y z is equal to x square plus y square minus z square. P is equal to 0 0 0. Now the question is that, think about it, let me know. Now the question is that please think about it, let me know which one of this ABC possibly be true. So basically those who have studied the multivariate analysis, so possibly they understood that this particular question is somehow related with the implicit function theorem, right? So take your time and let me know what will be possible answer. Okay, please give a logically correct answer only. Okay, please take your time and let me know. Let me check that things are working fine or not. Please take your time and let me know what will be the possible answer. Hi Mustaq. Okay. So since you have joined late, so can you please confirm whether am I audible and is the screen visible to you?
Yes, yes, it is visible.
Thank you for the confirmation. So it seems you are a regular student. That's very good to hear. So do you have any doubt from the previous session, or do you have any other doubt?
No, no, I have no doubt.
Okay, that's good to hear. So, 1 minute. So here I have written the first question. Please read it and try to solve by yourself. Take your time. And in the meantime, if you have any doubt, please let me know. Okay, please try to solve this. Take your time. And if you are unable to solve, please let me know. And also, if you don't understand how to approach, that also please let me know. Okay, because this session is problem solving sessions. So try to utilize it as much as you can. So, Mustaq, do let me know. Are you able to attack this problem, or still trying to figure out how to do that?
No, no, I cannot able to solve.
Okay. So tell me one thing. Have you studied multivariate calculus? Just asking for curiosity.
A little bit.
Okay. So have you heard about the implicit function theorem?
Can you repeat again?
Uh, did you heard about implicit function theorem?
Uh,
Am I audible properly?
It's audible.
Oh, good. So it seems that you have not heard about implicit function theorem. That's okay. So okay. Okay. Let's wait for 2 more minutes. Try to solve it, or else I shall explain to you. Okay. So let me explain.
A little bit I know this statement actually. If
Yeah.
of it,
So basically, these statements lies under implicit function theorem.
f of x, y is continuously different when f belongs to C1 near a point AB. Suppose f of a b is 0 and d
Hmm.
partial derivative df of
Hmm.
dy of
Hmm.
ab not equal to 0 and there exist an open intervals around a say I and
Hmm.
another open interval around b say z. A
Hmm.
differentiable function y is equal to fx
Hmm.
defined on I then such that f of x comma fx is equal to 0 for all x belongs to I and f of a is equal to b and f derivative then f is derivative of f is
Hmm.
given by
Hmm.
minus of difference partial derivative of x
Ah,
and divided by partial derivative of df by dy f of f is function of x comma fx.
correct. 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 Absolutely right. So that's what basically you said. Then, this, that is very good. You have recognized it's somewhat connected to that. So that is very good. I must appreciate it. So now let's go to the solution. Okay. So the first statement, the given statement A, the statement A is not true. So the given statement is not true. Why I'm saying this? Because 1 minute. Okay. Why I'm saying this statement A is not A is true? Sorry, I mean statement A should be true. It is true. Statement A is true. How? So we have the function h of xy is equal to x squared plus y squared, right? And this function takes the value 2 at the point 1 comma 1. Okay, so we can choose row greater than 0 such that h is positive. I mean h is positive in an open row neighborhood of 1 comma 1. Okay, and if we put z to be g of x comma y, okay, which is equal to root over h x comma y. Okay, so this is a smooth function. Smooth function in b row 1 comma 1. Okay, and this follows that f of x comma y comma g of x comma y equal to 0. So for this first, for so 1 minute. So question A is the argument clear. For question A is the argument clear. Please let me know. So for question A is the argument clear. Mustaq, please let me know. Okay, so it seems that it's clear to you. So let's start the the point is that the option B is not true. Why I'm saying this? Because sorry, option B is not true. This is because sorry option B is true actually. Option B is true. Why? Because I mean due to the same argument as of A. Okay. Now go to option C. The option C is false. Let me know why it is false. Why option C is false? Let me know. Take your time and let me know why option C is false. Hmm. Hmm. Why this option C is false, Mustaq? Please let me know. Think about it. Let me know. Please take your time. Let me check the recordings properly. Okay. So the reason the option C is false, why? Because I mean, basically, from the hypothesis, it is clear to force to take G to be plus minus root over x square plus y square, okay, which is no doubt to be continuous, no doubt to be continuous, but of course, it is not a C1 function in any neighborhood of 0, comma 0. So that's why the option C is not correct. So only option A, option B is true, option C is false. Okay. So Mustaq, is this argument clear to you? Please let me know. So please uh, go through the argument one time. I shall be back within few minutes. Please take your time and let me know if you have any question doubt. Okay. Please go through the argument one time. Okay. So, so, do you have any doubt or any question regarding this question one? If not, then we can move on to the next question number two. Okay. Sorry. So the question two is a true false question. It is a true or false question. The question is that compact subspace of a topological space are always compact. Compact subspace topological spaces are always compact. So it is true or false? Think about it. Let me know. Basically, first you need to figure out by some examples. Okay, so see this particular example. If you want to, this particular example is always false. Sorry, always true in the metric space. Okay, because in metric space, compact things are closed, and closed are the compact. Okay, so you need to consider some spaces which are not metric space. So try to construct a counter example. Okay, so let me check the word properly or not. Okay, things are going properly. Okay, so in this question, it is true. Is it true or false? Sorry for the convenience in between. There is a network issue. So show that compact subspace with topological is always compact. How to show that? Please take your time and let me know. Compact subspace topological is always compact. How to show that? So see, it is so first of all, when these things are true in the metric space because metric space in the metric is a compact set is a closed and closed or compact is compact. It is not true in general topological space. Why I'm saying this? In topological spaces, it is false first of all. Okay, in topological spaces, singleton sets are always compact, but need not be closed sets. Why? Because if X is a Hausdorff space, then every compact subset is closed in X. So is this clear? So argument is that singleton sets are always compact, but they need not to be closed. Why? Because if X is a Hausdorff space, then every subset of X is closed in X. Okay, so that's why the reason. Okay, so is this clear to you, Mustaq? Is this clear to you, Mustaq? Okay, I hope so. It is clear to you, Mustaq. Okay. Okay, now go for the next question. Let me dive to the next question here. The question is that which one of the following is true? The question is which of the following are true for Q with usual topology? Sorry, the options are locally compact space, option B a Hausdorff space, option C is second category, option D is normal space. Okay, so please think about it and let me know which one of is true and which one is not true here. I shall wait a few moments. So Mustaqil, please let me know, are you able to figure this out? How to do that? Okay. So, hmm, so the solution is as follows. Okay. The answer will be B and D itself. B and D only. Why I'm saying this? Answer will be any. Why? Because we have Q is equal to union n singleton Qn. Okay, where this Qn is an enumeration of Q. Okay, now each Fn is a closed set with empty interior. So Q is not second category. Now being Hausdorff, it is not locally compact. Else it will contradict theorem 2.18 which has been taught in class. So yeah, so that is the argument. So the argument goes as follows. Since Qn, sorry, Q is equal to union of Q and Q is an enumeration of Q and each Fn, Qn is a closed set to the empty interior, so Q is not second category. Now, being house drop, it is not locally compact. Else, it will contradict the theorem 2.18. So, this is the argument. Is this argument clear to everybody? Please let me know. So, yeah, so that is the thing. So, Mustaq, are you able to understand this argument? So, okay. So now, um, okay, so there is another way of doing the same. Hold a moment, please. So there is another way of doing the same. There is alternative solution, alternative way. The way is as follows. Given any neighborhood u of 0, there exists R belongs to QC such that minus R comma intersection Q subset of U. Now note that minus R comma R intersection Q is a closed sub of Q. So U closure is compact. Then minus R comma R intersection Q is also compact. But however, we should not forget that minus r comma r intersection q is equal to union of n belongs to n minus nr by n plus 1 comma nr by 1 plus n, which is an open cover having no finite subcover. So this is the argument. Okay. So this argument tells what? Suppose u is a neighborhood of 0, then there exists r which is not rational, such that minus 1, which is such that minus r comma r intersection q subset of u. And note that minus r comma r intersection q is a closed subset of q. So u closure is compact. This tells that minus r comma r intersection q is also compact. However, this union is open cover, so having no finite subcover. So that is the argument. Is it clear? So please go through the argument once and let me know is it clear to you, or else then we shall move for the next question. Let's take our time and let me know. I stay back in a few moments. Okay. Okay. So I have this argument is clear to everybody. Now let's move on the next thing, namely the next question, namely the following. What is that? Okay. Let x be 0, 1, 2, dot dot dot, n is equal to 0 with the topology generated by the subbase 0, comma n belongs to n. Then x is a locally compact space, second is T1 space, third is compact space, and D is Lindelof space. Okay, so these are the four options. So the x is given with the topology generated by subbase 0, n, and x is the locally compact T1 compact Lindelof. Now the question is what it possibly be. Okay, so think about it, take your time, let me know. Hmm. Please take your time and let me know. Hmm. Hmm. So, hmm. So the correct answer will be, sorry, the correct answer will be D only. Why? Because first, why option A is false? Why option A is false? That is because the element 1 belongs to X and the open set 0, 1 containing it, there is no open subset V of doubleton 0, 1 containing 1 for which V closure subset of 0, 1 as singleton 1 is not open and closure of 0, 1, this contains whole of n. The option B is false. Why? Because this is false. since this is false since the open cover 0n does not have finite subcover. Option C is false. So the same, okay. C is false because there does not exist no open cover, no open subset of X containing no open subset of X containing one that does not contain cheetah. Okay. And why the option D is true? True as X is countable. Okay. So yeah, so that is the argument. So yeah, so please take your time and let me know. So let me so what is the question? The question was that so X is equal to hmm, 0 1 to n union n equal to 0 with the topology 1 minute. Take the obvious ones. Huh. With the topology generated by the subbase 0 comma n, then show that X is locally compact space. Okay. Hmm. So hold on, please. Hmm. The T1 is space and X is so look so the first option is not correct because since 1 belongs to X and open set 0 containing it, there exists no open set V of 0 1 containing 1 for the for which V closure subset of 0 comma 1. Okay. Now as singleton 1 is not open and closure of 0 contains the whole of n, so that is not true. And option B is false because the open cover 0 comma 0 n does not have finite subcover. Okay. And option C is there does not exist any open cover of X containing 1 and that does not contain 0. Option D, so X is countable. Okay, so this is the argument. So that is the full argument, and option D is true because X is countable. Okay. So that is the thing. So yeah, okay. So now, so I hope this argument is clear to everybody. Now let's move on to, just hold a moment, please. Seems this 1 minute. Now let's move on to question number 5. What this question 5 tells is that it's a true or false question, okay? The question is that every G delta set in a compact Hausdorff space is the precise zero of a continuous function. Every G delta set in a compact Hausdorff space is the precise zero of a continuous function. That means what? If we take a G delta set, we shall able to get a continuous function whose zero set is nothing but the given G delta set. Okay. So yeah. So think about it. Let me know how you can attack this problem. It's not difficult. Take your time. Let me know. Hmm. Hello, 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 hello. Okay, so hold a moment, please. Okay, let me. Sorry, inconvenience. There's issue with the OS itself. I simply can't do anything for that. Hmm. Okay, hmm. So every J delta set in a compact house is precise zeros of a continuous function. How to do that? So it is true. First of all, it is true statement. Okay. Let A is equal to intersection n un be a closed G delta set in a compact Hausdorff space. In a compact Hausdorff spaces. These are normal. So X is a normal space. Now, using Udishan's lemma, there exists a functions fn x201 such that fnx is equal to 0 on A and fnx is equal to 1 on complementary. Then the function f summation n fn by 2 to the power n is the required function. Okay. So this argument. Please go through the argument once and let me know. Hmm. Okay. So, hmm, hmm. Oh, so, mm, hold on a moment, please. Just, just, uh, just hold on a moment, please. Hold on. Hmm. So, basically, how the development goes is follows. Every G delta is a compact Hausdorff space, the precise continuous function. Okay. Now, A is intersection of even with closed G delta is a compact Hausdorff space, which are normal, X normal. So, using the Ulyssian's lemma, there exists a function Fn from x to 0, 1 such that if an x equal to 0 on A and if an x equal to 1 on even complement. Then the function m is equal to suspension fn by x, a required function. Okay. So, this is the argument. Is this clear to you? Okay. So now let's let's move on to the next question. Let G be a topological group and X be a topo space. A continuous action of G on X is a continuous map from G cross X to X with G comma X goes to G multiplied by X. Okay, such that such that G dot H dot X equal to GHX and B is E dot X equal to X. Okay. So Anyway, so these questions are regarding the topological groups. Okay. So anyway, the see, I mean, particular this question is not. I don't think this 1 minute. See, I don't think this particular question is very much interested in topology. I don't think so. So I think it's better to avoid this particular question. Hold on. So E dot x equal to x and use bare category theorem. There are some many important things people would like to know. Okay. So the point is that this particular question is not that point of interest right now. So I think it's better to leave the question for the time being. Okay. So now let's hmm, so um, okay. So this so the assignment one is solved. Assignment one MCQ done. Now let's move for assignment two. Subject assignment to subjective questions. Okay, hold for a moment. Let me just hold a moment. Is there an issue with the OBS settings? Okay, one. Hold a moment, please. Okay, it is fine. There is nothing to do, I guess. Okay, so hmm. So now let's. So it's a um. So now let's move on to the subjective assignments. Okay, subjective assignment two. Okay. So 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 there are a few definitions on the go. Okay, few definitions on the go. So first definition is called sequential space. Okay. What this tells is that a topological space is called a sequential space if it satisfies the following properties. If it satisfies the following properties, namely a subset of X is open if and only if every sequence Sn in X which is converging to some point in A is eventually inside A. Okay. So what does this tell us? A subset of X open if and only for every sequence X in X which is converging to some point in A is eventually inside A. So hmm. So show that. Now the question is that show that a sequential space X which is Hausdorff belongs to CG, that is X, is compactly generated. Okay. So think about it and let me know the answer. Take your time and let me know the answer. Okay, Pustak, are you able to figure out any kind of argument for this question? If yes, please let me know. Hmm. Hmm. So, so basically, how to do that? Hmm. Okay. So, so the argument goes as follows. If not, there is a subset F subset of X which is closed in Kx but not in X. Put U is equal to X minus F, which is not open set in X, which is not open set in X. Now, since X is sequential, so since X is sequential space, so there exists a sequence Sn in X which converges to a point in S belongs to U. Okay, but the sequence is not eventually in U. This means there exists a subsequence. This means what? This means there exists a subsequence SNK where inside F And clearly, this subsequence converges to S. And if we put and if we put mm, K is equal to yes union yes and K, then K is compact subset of X. And therefore, K intersection F is closed in K. Okay. And this means what? This means yes belongs to F, which is absurd. So is the argument clear? Please let me know. Is the argument clear to you? Please let me know. Basically, in this argument, what we have done, we basically have done nothing extra. Apart from using the fact that is sequential criteria, we basically use only the fact that that sequence basically use the fact that the sequence have a subsequence, okay? And then we prove the rest of the thing, okay? So is it clear? Please let me know. Take your time. Is the argument clear? Please let me know and take your time. If this argument is clear to you, then let's move on to the next. Next what? Next statement. That I mean, so I'm writing down this statement. Uh, I'm writing down this statement as follows. Hold a moment, please. Okay. Hmm. So let me write down the statement only. The question is that does does there exist a non-compact space with a compact dense subspace? The question is that does there exist a non-compact space with a compact dense subspace? How you can approach this problem? Okay, before this, those who has not done the first problem, uh, please go through the first problem, then only start the second problem. Okay, please go through the first problem once. Okay, so or and who has done all these things, please start with the next problem. Okay, so yeah, the last one is what? 551. Just hold a moment. Mm. Okay, so now, so I have the first problem that you were. Now the question is that does there is a compact space, compact dense subspace? That's the question. So the answer goes as follows. The answer goes as follows. Okay. So see. So if we consider the space X to be 0, 1, 2, equal n, then 0 with the topology generated by the subspace 0 and n belongs to n, with the topology generated by subspace 0 and n belongs to n, then X is not compact as the open cover double tone 0 n belongs to n does not admit any finite subcover. However, 0 is a dense subset of X and it is compact as well. So yeah, so that is the argument. So what this argument tells that, so we so consider space X to be 0, 1, 2, 2, dot 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 with the topology generated by the subspace 0 n. And X is not compact as the open cover 0, 0 n does not admit into finite subcover. However, 0 is a dense subset of X and it is compact as well. So yeah, so this is the argument. So basically here what we are doing, 1 minute. Basically here what we are doing is the following, that x0, 1 to n with the topology generated by subspace 0, n, and X is not compact as the open cover 0 does not admit any finite subcover. But 0, n is a dense subset of X and it's compact as well. So that's why the whole thing follows. Okay. So this is the argument. Is it clear? I hope it is clear to everybody. Hmm. Okay, so now, hmm, so now the next question is as follows. So next question is that, So the next question is that, hmm. So x comma d be pseudometric space so that every closed subset in it is a G delta set. XG based pseudometric show that every closed subset in it is a G delta set. How to do that? Hmm. Hmm. So, okay, please think about it. Let me know how you can approach this particular problem. Then I shall explain to you. Okay. Please take your time. Let me know. So, okay. So, see, if B closed sub of x comma tau delta. Okay. Now, consider the function f x to r given by fx equal to d of f comma x is equal to infimum of dy comma x. Y belongs to f. Okay. First, we claim that f is apart semi-continuous. So this can be done. This can be done in different way. One is to appeal the, so there are two ways. One is by elementary method. One is elementary method, okay. And another method is by choosing the metric y goes to dux. And another method is the some kind of analysis trick. we are going. But anyway, this function is upper semiconductor. This is the HW. Try to do it by your own. We are not going to into that. Okay. So we can therefore we can define UN to be all those x belongs to x as the dfx. This is 1 by n. Okay. Open for all n. Now we claim that f is equal to intersection un and LHS subset of RHS. Okay, is obvious. Now, if x belongs to RHS, it follows that d of f comma x equal to 0. Then by definition, hmm, so by definition of infimum, for all n belongs to n, there exists xn belongs to x such that dxn comma x less than 1 by n. That means xn goes to x and hence x belongs to f closure equal to f is equal to LHS. So this is the full argument. Is this clear? I hope so. So what we have done here. So basically we have shown that so XD pseudometry space, we are going to show that every closed subset is FD G delta set. Now we are considering F to be the closed subset X comma tau delta, and we consider F X comma R and Fx equal to D of Fx. We are claiming that F is upper semiconductors. This can be done in different ways. So there are two possible. One is elementary method y goes to dyx. Another is un is equal to x belongs to d of f comma x is the one. This is open for all. Claim f is equal to intersection un. Now, LHS subset of RH is obvious. If x belongs to RHS, by definition, the infimum is x, and this tells that f belongs to RHS. Okay. So yeah, so that is the argument. Please let me know, is this argument clear to you? Please let me know, is the argument clear to you, or else we shall move for the something next. Hmm. So I hope this argument is clear to everybody. So let's stop here. Let's end the session here. We shall meet on the next upcoming Saturday. By the meantime, if you need out any question, please don't hesitate, drop an email to me. As soon as I get an email, I shall get back to you as soon as possible. Okay. Thank you. I am leaving the session.